So we'll just move forward from here. That is, there are a few important points here to understand. Let us try and understand that. So important points, what I wanted to mention are whenever we say difference, the difference of sets for any sets A and B, for any sets A and B, the difference A minus B is defined as A minus B is equal to X such that X belongs to A and X does not belong to B. Why we are having that A minus B? Why X does not belong to B? Because in A we are subtracting the B elements. So X belongs to A minus B implies that it means that X belongs to A but does not belongs to B. And regarding the previous point of discussion, operation of sets, at that point we just try to refer again. I think because here we can have some doubt. Let A and B be two sets, then the A is equal to B, and we have to prove it here that A is equal to B. The double implies A is a subset of B and B is a subset of B. If A, so obviously whenever it's both a subset of each other, so we can say A is equal to B. Now, which is incorrect is very important to understand here. 2 belongs to A. I will not say 2 belongs to A because in brackets 2 is written, which is an element of A. Hence, it is incorrect. Is a proper subset of, so they are saying that 2 in brackets is a proper subset of A. Initially, it looks to be correct. It's a proper subset. So a set can be a proper subset whenever that concept is used here. So let us go back. Proper subset. We need to write it again in a set form. One more bracket we have to write every time. That is the learning we can have. A is having this elements 1, comma in bracket 2, 3, bracket close, comma 4. Then which of the following is true? 2, comma 3 belongs to, in a bracket, it belongs to A. So is a true statement. Belongs to, we can say. Whenever proper subset we are saying, in that case, whenever we are saying proper subset. So in brackets 2, comma 3 belongs to A is okay. Is a proper subset. In that case, element can't be a subset. A set can be a subset. Right? So that is the logic. A and B are sets in that case. Actually, subset case arises whenever we have a set and belongs to, we can easily write. That is a concept. It's a very good concept, I would say. So in this case, A is a subset. In example 1, if you see A is subset of B, not equal to B. So is a proper subset of B, we can say here. But in the case of Example 4, we can say 2 comma 3 belongs to A. It is not a proper subset because again a set notation, we have to keep it here. Element is already having a bracket. We'll have to keep it again one more because set form you have to convert, right? That is the logic. There's a very, very good logic, I would say. So this we have seen earlier. Z dash will be all the positive integers and set of all negative integers, Z minus and so intervals as subset of R. Let A comma B belongs to R and A is less than B. We can say close brackets X is greater than equal to A and less than equal to B. In close bracket means A comma B is a close brackets and X belongs to R such that X is greater than equal to A and less than equal to B. Open interval, we have A comma B or both intervals are open, X is greater than A and less than B. Right half open interval, right half open is very simple, like right half open means right is open, left is closed, and left is open, right is closed. Like this we can mention. So both open, dots are not filled up, and both closed, dots are filled up, and right open, left open. We can write like that. Length of each of the interval of any of the interval, that is A comma B, closed, open, right open, left open, is B minus A. Examples of intervals, what we can say? What are the examples? The set of all subsets of a given set A is called the power set of A, denoted by PA. If NA, number of elements of A, is equal to M, then number of elements of A is PA is equal to 2 to the power of M. The set of all subsets of a given set A is called the power set of A, denoted by PA. So if number of elements of A is N, then power set, number of elements of the power set is to the power of N, which is a very important case, I will say. The first question is write down all positive subsets of A, bracket 4. Obviously, all the possible subsets are 5 and 44. Number of elements of A is 1. Number of elements of the power set is 2 to the power of 1, 2. So let us do some other type of questions. Write down all the possible subsets of A. So in this case, write down all possible subsets of A. will be equal to 1 comma 2 comma 3. Example number 4, if you're looking up, write down all possible subsets of A. We have 1 comma in bracket, and again our bracket is there 2 comma 3. A contains two elements, namely 1 and this particular element. Let this is B, then A is having 1 comma B. Uh, we have what are the other power set? Will have pi. We'll have pi. We'll have 1 as the 1 in the bracket, B in the bracket, and 1 comma B also in the bracket. So we'll have 4. Total the 4 elements would be there in that. So which is logically okay. So let us go further. The further means write down all possible values of subset of A. So we have written here pi will be included every time, and every set can be separately written, and in combination also we can write. That's why it is to the power of that number of elements of set, and here it is to the power of 2, that is 4. Write down all possible values of the subsets of pi. Pi is only one subset, that is namely pi. So therefore power set will be phi has only one subset, namely phi. So therefore power set of phi will be only phi as the element here, and will not say here 1. How many elements are there? There is no elements. Subsets, the same subset, that's why. Element is 0. That is the reason why we have to the power of 0, that is 1. Equal sets. Two sets A and B are said to be equal if every element of A is in B and every element of B is in A, and we write A is equal to B. And here we can say that A and B do two sets, then prove that A is equal to B. A is a subset of B and B subset of A, then we can say A is equal to B. Okay. So this we can easily say. So what else we are planning right now? So here in this case, what is incorrect? Let us see. A is having this particular elements, which are the following are incorrect statements. So 2 belongs to, you can't say that that's incorrect. 2 is a in a set form, is an element. So it is a proper subset, I will say. In that case, I will have to keep it again here. So it is incorrect again. So 1 comma 2 again for that that is required. 3 comma 4 is a proper subset again for that the same thing. And for that also again the 1 comma 5 in brackets. So obviously in this case this will work out because 1 comma 5 are the elements and we have written already in the bracket, so it is a proper subset. 5 belongs to, does not belongs to A. 5 does not belongs to A. So in the sixth question we have 5 as a uh, in curly brackets. 5 in brackets is proper subset of A. 5 does not belongs to A. 5 does not belongs to A. So question number 6 is a better question, I would say, in this case. Question 6 is much better, I would say, in this case. That is why it is a better question. Question 6, that is 5 in bracket is is a proper subset of A that we are saying. But what we are finalizing here in this case is, since 5 does not belongs to A, okay, 5 does not belongs to A, is not written as 5 does not 5 is belonging to A, so not an element there at the moment. So 5 does not belongs to A. So when we're writing 5 in brackets is a proper subset of A is incorrect, while 5 is a proper subset of A is correct. So this part again we will have to review slightly for the subset case, because 5 again is a point of discussion right now. The empty set is a subset of every set. Empty set is a subset of every set. A be any set and 5 be the empty set. 5 is an empty set already. Since 5 contains no element at all, so there is no element of 5 which is not contained in A. So 5 is a proper subset of A. 5 is already a set, empty set it is. So that is a concept. So that's why we don't have to write separately there. Okay, separate writing form is not required. So 5 does not belongs to A, but it is incorrect. So if you write just 5 is a subset of proper subset of A is correct because it belongs to everything. Initially 5 belongs to A we will write because that is a logical statement. Does not belong, we can't write, or okay, we can write that because this is mentioned. 5 does not belongs to A, but universally 5 is the proper subset of A, but 5 in brackets is not there. We don't have to write like that. 2, let us say for the second one, 2, 1 belongs to A, 1 is a proper subset of A, okay. So it is correct answer. And for the case of 2, 1, 2, 3, 4, proper subset. So that is incorrect. Operation on sets we are just trying to understand now. That's we will go further. Operation on sets, obviously A union B will be X belonging to A or X belongs to B. X is such that therefore X belongs to A union B. Double implies X belongs to A or X belongs to B. The union of two sets A and B denoted by A union B is the set of all those elements which are either in A or B or in both A and B. We can have some element where A can be, the element can be an A or a B or A and B both. It is completely possible because it contains the intersection part also, right? So that's why whenever we say A or B, so in that case we can write like this. So A is 3, 4, 5, 6 and B is this. What is the union? So union will have contain all the elements of 3, 4, 5, 6. 3, 4, 5, 6, 8, 10 will be there with us. And similarly, what is the next part? Similarly, we can say A is equal to X such that X is a prime number less than 10. X such that X is a prime number less than 10. And B, which is equal to X such that X uh, belongs to N. X is a factor of 12. X such that X is a prime number less than 10. X such that X is a prime number less than 10 and B is again a set where X says that X belongs to N. X is a factor of 12. Close the bracket here. We need to find the A union. So A is we're having the prime numbers are 2, 3, 5, 7. For B we have is a factor. So obviously factor means we can write all of this and union will be containing all of these together. The union of N sets is denoted by union will write the symbol I is equal to 1 to N. Now whenever we have multiple sets, in that case, what is the feature we were trying to understand? The union of N sets, that is A1, A2, A3, A4, A5, An is denoted by A1 union A2, union A3, union A4, union An. And then you can say this. So union of all the sets, that is A1, let us say we have multiple sets A1, A2, A3, A4, A5, A6. We can see on the screen that we have multiple sets. In that case, what we can say? We can say that the complete part, the union of n sets A1, A2, A3 till An is denoted by A1 union A2 union, and we can also denote separately with a single symbol that U symbol will write. And that is a good logic. Union of I is equal to 1 to n AI. The intersection of two sets A and B is denoted by A intersection B, set of all elements which are common to both A and B. Thus, A intersection B is equal to X such that X belongs to A and X belongs to B. Also, I can say X belongs to A intersection B means A and B it will also both belong, right? It will not be or here because it is a common part. X does not belong to it doesn't mean that it means that not belonging to each of them. So let us go for a question that is question number 7, example number 7. Uh, A is a set with x such that x is equal to 3n and belongs to Z, and B is equal to x such that x is equal to 4n and belongs to Z. Then we need to find A intersection B. Whenever we need this in this case, so we have n belongs to Z, that is a integers. In the case of integers, x is a multiple of 3, so obviously we have a few values of that. Basically, we need both common here. Multiple of 3, multiple of 4, so we need x is such that x belongs to Z and x is a multiple of both 3 and 4. And in that case, obviously, we have a LCM we can take, that is a multiple of 3 and 4. We take multiple of 3, the least common multiple will be 12. So x is such that x belongs to Z and x is a multiple of 12. So x is so that x is equal to 12 and belongs to Z. Hence, A intersection B will be 12n here in this case. So let's say A is equal to 2 comma 4 and B is a right open set with 3 in the close bracket comma 5. We need to find A intersection B in this case. First, we need to define this set in a proper fashion. So A is equal to 2 comma 4. X is such that x belongs to real numbers and x is greater than 2 and less than 4. Obviously, it is 3 only, one value. And similarly, B is a right open, right open interval where we have x such that x belongs to R. X is equal to or greater than 3 and less than 5. So we have two values here in this case. So what we can say here, we can say that A is equal to 2 comma 4. So x is such that x belongs to real numbers. Now, what is the intersection in this case? Intersection wise, it is different, looks like. Why it is done like this? So A is equal to 2 comma 4 and B is equal to 3 comma 5. Here in this case, what I can say is an open bracket. So obviously x is greater than 2 and less than 4, and x is greater than or equal to 3 and less than 5. So we have here, this case needs to be analyzed properly. If A is having two elements, that is 2 comma 4, and B is having, so obviously here we have closed bracket here from the elements 2 comma 4. Two elements are there, 2 comma 4. Here we have 3. And from this side to this side. Okay. 2 comma 4 we can written like this. This and this is okay. This is closed. So elements are like this in this case, I will say. And here 2, 3, 4. That is the reason why 2 comma 4 is an open bracket. So that's why, because this is an open bracket, that's why the elements will be 2, 3, and 4. The elements will be 3, 4, 5. So 3, 4 is the answer here. And I can write like this. That is correct. So the intersection of n sets A1, A2, A3 is denoted by intersection symbol is there, then I is equal to 1 to n AI. That we can write in the same the way we have written the union, we have written the same format. Two sets A and B are said to be disjoint if they're not joined together. If intersection is phi, two sets A and B are said to be intersecting if is not equal to phi. So example 10, if you are forcing, give examples of three sets A, comma B, comma C, where intersection of A and B is not equal to phi, not equal to phi, not equal to phi, all of them. And so 1, 2, 2, 3. Okay. So obviously intersection B has something there. You can take an example of A 1, comma 2, 2, 3, 4, 1, 3, 5. So we'll have something there every time. Firstly, we need to take A intersection B is not equal to phi, B intersection C is not equal to phi, and A intersection C is not equal to phi, and A intersection B intersection C is equal to phi. That we would take. Give an example of three sets A, B, C, such that then A intersection B, consider the sets. I mean, take an example here. Difference of sets obviously is a very good concept. So A minus B is equal to B values will be deleted here. So X belongs to A, but X does not belongs to B. Somebody, symmetric difference of two sets. The symmetric difference of two sets A and B is denoted by A symmetric B is A minus B union B minus A. Symmetric difference of two sets, we write a triangle notation is there. A symmetric B, so will be equal to A union B plus A minus B union B minus A. So here in this question, we need to find the symmetric part. So A minus B will be AC, and here we have FG. So A symmetric B is A minus B union B minus A. So that is the method. So what else we are trying to understand from here is complement of a set. Let U be the universal set and A is a proper subset of U. Then complement of A denoted by A dash or U minus A is defined as A dash or A complement will be X as that X belongs to U such that X is not belonging to A. X belongs to A dash. This double implies X does not belongs to A. That is the logic of complements. So X, if you see this question, if A is a proper subset of U, then we need to prove U complement of U is equal to phi. What is complement of U, that is X belongs to U such that X is not belonging to U, is phi. Complement of U, X belongs to U such that X does not belongs to U. It's phi, and X belongs to U such that X does not belongs to phi. So it will be U. Double complement will give the same set every time. Okay. And union with the A and its complement union will give the complete set, universal set. A union, A complement will be union, will be U will be the set here, and A and it is phi. A and A complement intersection will be phi every time. So that is a logical or important case, I would say, laws of operation. So in them, potent law, union of the same set will be A, intersection of the same set will be A again. Identity law, A and union with phi will be A. Intersection with U will be A, you use the universal set. Phi and U are identity sets, elements for union and intersection of sets respectively. Union B will be B union A. Similarly, intersection B will be B intersection A. A union B union C can be written as the union of A and B union C. Associative law for union of sets. Associative law for intersection of sets. A intersection B intersection C. So A intersection B intersection C. So let X be a arbitrary element of A intersection B intersection C, then X belongs to A intersection B intersection C. X belongs to A intersection B and X belongs to C. So we have one more theorem that union distributive law obviously is a very important. I think it's a bit different distributive law of unions over intersection. A union B intersection C will be A union B intersection A union C. A intersection B union C. A intersection B union A intersection C. These are the distributive laws which are important. De Morgan's law is an important part. So A union B complement will be A complement intersection B complement, and intersection B complement will be A complement union B complement is just opposite. The result is opposite here. So that is the thing. So A is a subset of B. It implies that B complement is also a subset of A complement. Similarly, we have A minus B. So for A minus B, we have A intersection B complement. A minus B intersection B is phi. A minus B union B minus A will be A union B minus A intersection B. So like this, the things are there. A minus B is A, obviously, so A intersection B is 0. This is absolutely correct. And if A union B is equal to A intersection B, then obviously A is equal to B. In that case, if both union and intersection is giving the same result, so both are equal. A is a subset of B, then for any set C, C minus B is a subset of C minus A. A union A intersection B is A. A union A intersection B is A. An intersection of A union B with A is A. Now for any set, again, we have a condition here. A intersection B union A minus B is A. Intersection A intersection B union A minus B, that is A only. So this will be A union B minus A, that is B only. So it will be A union B. A intersection B complement is phi. B complement. Then in that case, A is equal to A intersection B. If ABC has set such that union A and B and A and C are equal, and A and B and A and C are, then B will be equal to C. De Morgan's law is important here, obviously. So De Morgan's law says that A union B intersection will be A intersection A complement, sorry, A union B complement will be equal to A complement intersection B complement, and A intersection B complement will be A complement union B complement. A minus B union C. So A minus B intersection A minus C. So a lot of other stuff is there. That is A intersection B minus C is A minus C intersection B minus C. Let us say A and B are B2 sets. And A intersection X, B intersection X is phi. A union B, A union X and B union X for some set X, then A is equal to B. Now A and B, we research the A intersection X will be equal to B intersection X is phi. If they're equal, then A will be equal to B obviously. P P probability is power set of A intersection B will be equal to power set of A intersection power set of B. Uh, Power set of A union power set of B is a proper subset of power set of A union B. Power set of A is equal to power set of B, then A is equal to Venn diagram, so it is important part. We'll pause it here for some time.